Okay, the next discrete random variable is the Poisson random variable. With what we call the rate lambda. It has to be a positive number. It doesn't have to be an integer. And our PMF is defined non-zero for any non-negative integer. So we think of x as being the number of events that have occurred in some time interval usually. So probability, although it could be spatial or other things too, but we'll think of it this way as the number of events of a certain type that have occurred in a certain time interval. And we say no events could have occurred, 1, 2, etc. So the probability that k events have occurred is given by this. It's e to the minus lambda, lambda to the k over k factorial and 0 otherwise. We'll see where this comes from in a second. We can check that the sum over all non-zero probabilities for k is indeed 1. This just comes from this being equal to e to the lambda from the Taylor series. So any lambda, as long as it's positive, will give me e to the lambda here, even if it's not positive actually, and I will get e to the lambda times e to the negative lambda, which is 1. So everything looks good. Where does this come from? When do we use it? So the idea is, so let's write the first thing down about the, I'm tilted here, about the first thing. So the idea is x is a number of events of a certain type that occur in pre-specified interval of time. And we could say with a rate of lambda. In fact, in this case, x will be an approximation for a binomial NP-RV if lambda is equal to NP. Here's the idea. Here's my interval here. Say this is interval, the unit interval, say. It doesn't have to really be, but say it's the unit interval. And lambda is a rate. So lambda is the number of events in the unit interval. Well, if I break these down into small little cells here, all equal cells, and I consider that it's reasonable to suppose that an event occurs in any cell independently of the others. Say we have n cells, and probability event occurs in any cell is independent of it occurring in other cells and constant. Okay, so then I can look at this as a binomial random variable. So let's suppose we let y be then equal to binomial NP equals number of cells that had an event. Then y can be approximated by x, which is Poisson lambda, if lambda is equal to NP, especially, sorry about that, especially when n is large and p is small. So lambda is, say, moderate. Although all these things have to be sort of understood mathematically, and this is just to give you a general idea. So the idea is I have this interval, and I want a random variable representing the number of events. Well, I can think of sectioning the interval into a bunch of tiny little cells and then modeling it with a binomial random variable, which has a very small probability of occurring in each cell. But when I add all the cells up, I get something that's moderate. So that's to give you the intuition behind it. Okay, we can then let's actually look at a little example here and check the numbers, and then we will demonstrate why this works mathematically. So suppose as an example, machine produces 800 items in a day, per day. The probability that our randomly selected random item is defective, suppose this is equal to 1 out of 200. Now you see, for one thing, I'm not talking about a time interval so much, I'm talking about 800 items, but you can think of these as cells as well, like each item, say every 5 minutes an item's produced, okay, and I have, so, I have a day, which is whatever 800 divided by 5 is pretty big. But it's whatever it is, and then I could think of the time, and you could see the analogy. So let's let x equal number of defects per day. Okay, and I could model this with a binomial or a Poisson. So suppose we say x is binomial 800, 1 over 200. And find, let's say find px less than 2, strictly less than 2. It's exactly the same problem I did in the notes. So if we go like this route with the binomial model, we have probability x is less than 2 is just equal to the probability x equals 0 or x equals 1, but they're mutually exclusive. So probability x equals 0 plus probability x equals 1. This is easy enough to do. I need all of them to be successes. So I have 199 over 200 to the 200th power, to the 800th power, plus, now, I could have any one of the 800 could be a defect. So I have 800, choose 1, and I know I need 1 defect. That's 1 over 200. And I knew that I need the rest to be good. So I have 199 over 200 to the 799. So for one thing, you can see this is not a pleasant calculation to make, and it's actually pretty easy. Like if I took bigger numbers and I wanted more probabilities, it could be pretty nasty. So I'm here, and I do this, the R handles this perfectly. I have 0.09103 to 5 digits. But we could use the approximation, so 2, using Poisson approximation, lambda approximation, we set lambda equal to NP, so should be equal to 4. So in other words, the rate or the average in the long run is 4 defects per day. So I make that the rate, and then I have probability x is less than 2. Again, it's just the probability x is 0 or 1. But I'm going to use the other PMF now. So probability x is 0 is e to the minus lambda times times lambda to the 0. So it's technically 4 to the 0. over 0 factorial. And now probability x is 1 is e to the minus 4, 4 to the 1 over 1 factorial. This is equal to e to the minus 4, of course, can factor, and I have 1 plus 4, which is equal to 5 over e to the 4th, which is equal to 0.091558. Okay, so here's the error. So it's very close, right? It's very close to within. Order of magnitude of error is 10 to the minus 4. So very good. Looks like it worked. Why does it work? We will see on the next video.